Hi there, people, and welcome back to the ViViMaT channel. Our next speaker today is Raisa Rudge. People, get ready for a treat. This woman is an excellent scientist, a brilliant and witty speaker, loves puns, and she specializes in biotribology. Let's just say that it's unlikely that you'll have seen anything like this before. Raisa finished her bachelor's and master's in chemistry and chemical engineering at Leiden University and Delft University of Technology. She then went on to do a PhD in soft tribology at Wageningen University, at the end of which she spent 1 year as a guest PhD researcher in the group of Jason Stokes at the University of Queensland, Australia. She just defended her PhD with flying colors last Thursday. I was there. Although the title of her talk sounds delicious, be aware that a lot of it will revolve around spit. Raisa, fire away. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, one is spit tribology. Yup!
Hi everyone, my name is Raisa. I recently finished my PhD at Wageningen University in the Netherlands. And during my PhD, I did a bit of an exchange period in Australia at the University of Queensland, and I'm currently actually still in Australia. And I'd like to tell you about some of the work that I've done during my PhD, specifically on wine lubrication. So first of all, thank you for joining, having a look at some of the work that I've done. And I would also like to thank Stefan and the team for setting this up and for giving us a space to share whatever we like to share about tribology. So today, like I said, I will share some of the work I've done on wine lubrication, which is why I chose the title, Why is my Wine Dry? As I will be telling you more about the molecular mechanisms behind lubrication losses. And these lubrication losses are specifically related to certain foods we eat that can induce a dry mouthfeel. So like I said, my name's Raisa. Recently finished my PhD, actually just finished last week. And I did my PhD under the supervision of Joshua Dijksman at Physical Chemistry and Soft Matter in Wageningen, and with Elke Scholte at Physics and Physical Chemistry of Foods at Wageningen University as well. So essentially during my PhD, I was part of a soft matter group where we look at a lot of different things such as the rheology of fluids, of particles, etc., as well as develop new materials with interesting physical chemical properties. And on the other side, I'm part of a group where we're interested in the physics, the physics and chemistry behind the foods we eat every day, and also foods that are currently being developed. So I use this approach to finalize the results that I presented in my dissertation. So a little bit about me. I did my bachelor's in chemistry and chemical engineering at Leiden University and TU Delft in the Netherlands. My master's in chemistry, and I had some elective course in food technology at Wageningen University. And then my PhD in soft tribology at Wageningen University, as I just mentioned. And I finalized my PhD as a visiting PhD, or guest PhD student at the University of Queensland with Professor Jason Stokes. And at the moment, I'm still researching, specifically searching for new academic opportunities. So if you do see this and you do have an exciting academic opportunity, don't hesitate to contact me. So I'll give you a bit of an overview of what I've done, what I've achieved during my PhD and the different systems I've studied. So in the Netherlands, we get to make a nice little booklet that combines all the different chapters of the thesis. So this is the front cover that I designed, and the title of the thesis was A Slip of the Tongue, Tribology of Soft Surfaces and Complex Lubricants. So my thesis was split up in 3 sections. One of the sections focused on hydrogel friction. The highlight of that section was that we used a custom-made 3D printed tribometer, and we highlighted the effect of surface roughness of hydrogels on hydrogel friction. Some of this work is published as well, so you might be able to find it in case you're more interested in this. Then we had a section on particle lubrication where we looked at soft hydrogel particles, we looked at hard glass particles, and we looked at particles in suspension. So we combined both fluids and particles, and we had high viscosity fluids, low viscosity fluids, which actually gave some interesting results. And then we ended by looking at the applications of tribology, where we use different tribometers. We actually used 4 different tribometers and analyzed the results side by side. And what I'm going to tell you about today, wine tribology. So tribology is actually getting more and more popular in food science. We eat every day, multiple times a day, and we enjoy it. Some foods we enjoy, some we don't. And what we actually try to do as food tribologists is understand how the mouthfeel is related to the tribological properties of certain foods, often fluid or semi-solid foods. So what we try to do in the field of food tribology is translate different mouthfeels, such as creamy, smooth, slippery, and astringent. I'll be telling you more about astringency today. We try to translate this into numerical values. So if different people eat the same yogurt, they will all evaluate it differently. Whereas if we just measure the yogurt with a non-biased device, such as tribometer, we get something that might be a bit more objective and helps us understand how certain food properties are related to mouthfeel and tribological properties. But how do you do that? How do you measure that? How do you go from a human organ, such as the tongue, to actually measuring mouthfeel? So for this, you need to know a little bit about the in-mouth properties. The tongue or the in-mouth surfaces are all saliva lubricated, and saliva is actually a very interesting lubricant. I will tell you a bit more about that in a minute. So saliva actually consists of 99% water, so it's mostly water, and then only 0.3% mucins and proline-rich proteins. I will be referring to these proline-rich proteins as PRPs today. Saliva has very low viscosity, but also low friction coefficient, which is quite contradictory if we think about it in terms of Strybeck curve. Or if we compare it to water alone, water is depending, of course, on the surfaces you use, but in a lot of contexts, water actually has a relatively high friction coefficient. Whereas when we have 99% water with just a little bit of protein, this is able to decrease the friction coefficient by an order of magnitude. So this is essentially the system we're looking at. You have the tongue and the palate, and saliva is covering or coating these surfaces, which is what we try to mimic in a tribometer. So astringency, I've already mentioned it a couple of times. It's the dry mouthfeel you get from drinking wine or eating nuts, seeds. It's often plant-based foods, such as maybe cranberry juice or tea, actually also good examples. So all these foods contain polyphenols, these plant-based foods, and these polyphenols induce this dry mouthfeel. And metal salts are actually also able to generate this dry mouthfeel. So why it's so interesting to study this, it's because it's not entirely known if astringency is more a taste sensation, such as bitter or sweet, which is receptor-based and is something triggered by the brain, or if it's actually a friction-based sensation. So today I hope to convince you that it's actually a friction-based sensation. So this is our hypothesis. This is what we expect to happen in the case that astringency is a friction-based sensation. So we have a salivary lubricating layer and aggregating agents. These are the astringent agents. And this is how we measure. So we have saliva, like I said, different proteins present in saliva. And we measure different polyphenols, large phenols, smaller phenols, and we also measure metal salts. As I said, metal salts are also able to induce specific reactions when combined with saliva. So we use an atom-powered tribocell to measure friction in this case. And we use PDMS, polydimethylsiloxane pins. This is often used in food tribology. Why do we use PDMS? It's because it has similar properties to the tongue in terms of hydrophobicity and hardness as well. And you can also tweak the roughness to be similar to the tongue. In this case, we use a glass ball to mimic the hard nature of the palate. So we can control the torque and the normal force, of course. So we measure saliva, and then we add the aggregating agents, so the polyphenols or the metal salts, to get a better idea of how this influences the friction coefficient. We use a 1-to-1 saliva and astringent solution. The saliva we use is actual human saliva, and the astringent solutions, the amount of astringent solutions and the amount of astringent in the solution is actually based on actual foods, on the polyphenol content of wine. And we measure at 1 millimeter per second. That's related to the in-mouth speeds as well as the force we use here. So this is what a typical measurement looks like. We first measure saliva for about 600 seconds, after which we add the aggregating agent, the astringent agent, and this causes aggregation to take place. In this case, we have saliva plus epigallocatechin gallate, which is a component of tea. So here you can see that saliva gives a rather low friction. It also takes a while to establish a constant friction coefficient. And upon addition of the astringent agent, the friction coefficient immediately spikes. So this is a very quick reaction that takes place. And it's a friction coefficient of 0.3. So that's quite an increase in this case. And this is how we'll be representing this increase in friction coefficient. We'll be showing this as the bar chart here to give you a bit of an idea of how these differences look when comparing the different types of astringents. So for water, we see a very limited increase, and this increase is only due to the dilution of saliva. So if we add EGCG to saliva, we see the increase of 0.3, as I mentioned in the previous slide. If we add tannic acid, and again, we find an increase in the friction coefficient. So these two are large polyphenols, and they give an increase in friction coefficient when mixed with saliva. Next, we add alum, a metal salt. That gives a very limited increase in friction coefficient. Gallic acid, a small phenol, also limited increase, quite similar to water, and the same for caffeic acid. So the interesting thing is, we also looked at the increase in particle size. So the EGCG and tannic acid both give an increase in particle size as expected. However, alum does not increase the friction coefficient, but it does aggregate the proteins. So that was actually quite interesting to us as well, quite a mystery. So as you can see here in black, that's saliva alone. And when we add alum, an extra bump is formed, which shows that aggregation has taken place. However, in this case, aggregation does not cause a spike in the friction coefficient. So I've split it up in 3 categories. So for the large phenols, we find lubrication losses and aggregation. For alum, we find no lubrication losses, but we do find aggregation. And for gallic acid and caffeic acid, we find no lubrication losses and no aggregation. So here's a bit of an overview. So like I said, for large polyphenols, when mixed with proline-rich proteins, we found aggregation and lubrication losses. So it might be, I'm just going to take a second to explain how we actually did this. So for this approach, we used mucins. So these mucins are commercially available, and that's one of the proteins that's also present in saliva. And we used proline-rich proteins. These proline-rich proteins were isolated in the lab. And we measure these separately with the different polyphenols and the metal salt to figure out which one of these salivary proteins are actually reacting with the polyphenols. Now, this gave us an interesting overview. So for proline-rich proteins, we find aggregation and lubrication losses when combined with polyphenols. For small phenols, no reaction takes place. Metal salts, nothing happens with the particle size or with the friction coefficient. However, when we look at mucins alone, the large polyphenols are able to aggregate mucins and generate lubrication losses. The small phenols leave mucin unaffected, and the metal salts aggregate mucins and also generate a lubrication loss. So if we go back to actual human saliva, which is a mixture of proline-rich proteins and mucins, this explains what we've seen before. So proline-rich protein aggregation is required to obtain salivary lubrication failure. So the effect, I'm just going to go back to the previous slide. So what we've seen here, the fact that alum increases the particle size, but not the friction coefficient, that is related to the fact that mucins are aggregated by alum, but proline-rich proteins are not. So in the case that just mucins are precipitated or aggregated, no changes in the friction coefficient occur. So these are some of the mechanisms we hypothesized that are taking place. So for large polyphenols, it's known that they can induce hydrogen bonding and hydrophobic interactions with mucins and proline-rich proteins. So this explains why these large polyphenols interact with both mucins and proline-rich proteins. Metal salts, however, can only undergo electrostatic interactions, no hydrogen bonding, because they don't have the right chemical structure for that. And which is why these metal salts only are able to react with mucins and not with proline-rich proteins, as proline-rich proteins only have limited charge, and the mucins can readily react with these metal salts. So in a lot of foods, these lubrication losses, now that we know that astringency is related to lubrication losses, for example, for wine, lubrication losses are actually considered a quality aspect often. Yet not everyone enjoys this dry mouthfeel, especially when eating other plant-based products such as nuts or maybe tea. You're not looking for this dry mouthfeel. And then a lot of plant-based products are also used in what I like to call new foods. So oils, of course, are not that new, but also plant-based products, and they may contain traces of polyphenols. And then plant-based meats and plant protein powder, these are also generated from actual plant materials. So even though the protein is the main component that's needed, some polyphenols might be present as well, which gives the dry mouthfeel, which is something the consumer isn't always looking for. The next question is, can we prevent these lubrication losses? So we've looked into doing this using a hydrogen bond disruptor. So we have our PRPs and mucins. If we then add the polyphenol, we get aggregates. And if we add the hydrogen bond disruptor, as you can see here, this surrounds the polyphenol. And as it's surrounded by the hydrogen bond disruptor, it will be unable to react with the salivary proteins, which, if our hypothesis is correct, this should reduce the friction coefficient. So we had a look at this. We actually carried out the measurements with a hydrogen bond disruptor. In this case, we used HFIP, hexafluoroisopropanol, which is known as a strong hydrogen bond donor, which means that it readily surrounds or takes up all the spots of hydrogen bond donors, and in that way can disrupt the reaction between the polyphenols and the salivary proteins. So I'll show you an example of when we just measure proline-rich proteins, and we add the astringent agent, and the friction coefficient increases as expected. And then when we add the hydrogen bond disruptor, the friction coefficient goes back to where it originally was. And we've also tested HFIP on its own, and the friction coefficient of HFIP on its own is very close to that of water, which would be around 1. So this decrease isn't caused by just the HFIP, it's caused by the fact that the PRPs are back to their original state where they're not aggregated. We've also confirmed this by the particle size. The aggregates actually break down and we get the original particle size as well. So we saw this for proline-rich proteins and for mucins. So the addition of HFIP is, in this case, or the addition of a strong hydrogen bond donor, an effective way to prevent lubrication losses. Unfortunately, HFIP is not a food ingredient, but I will show you some examples of food ingredients in the last couple of minutes of this presentation. So like I said, we can reduce the lubrication losses by preventing the hydrogen bond. Another method we can prevent lubrication losses, besides limiting the interactions between astringent agents and salivary proteins, is by limiting the effect of the aggregates. So once the aggregates are formed, we will now try to reduce the effect of the presence of aggregates. So I'll show you some of the measurements we've done. So we use saliva, tannic acid as an astringent, and glycerol as a highly viscous medium. So we see that saliva alone gives rather low friction coefficient. We've seen that before. Add tannic acid, the friction coefficient increases. We've also seen that before. And then when you add glycerol, a highly viscous fluid, the friction coefficient actually decreases quite strongly and actually becomes lower than that of saliva alone. So the addition of this viscous component is also an interesting strategy and an effective strategy to prevent or to reduce lubrication loss. So this is the mechanism we think is taking place. So saliva, like I said, forms a quite good lubricating layer thanks to the salivary proteins. The addition of tannic acid, of course, disrupts that and causes an increase in the friction coefficient. Because they act as particles, these aggregates act as rough particles, which increase the friction coefficient. However, these particles have a certain size. And when you add glycerol as a viscous component, this can form a thick layer, a thick lubricating layer, by increasing the hydrodynamic pressure. And this causes viscous lubrication. And it seems that this viscous lubrication dominates the aggregation lubrication. So just by increasing that hydrodynamic pressure, separating the surfaces, the particles are no longer able to drive the friction coefficient, and glycerol actually takes over and decreases the friction coefficient. The nice thing is, glycerol is actually a food component. So this might be a strategy that can actually be applied in the food industry. So probably the moment many of you have been waiting for. A lot of abstract information, a lot of chemicals, different chemicals we're using. What does this mean for wine? Why is your wine dry? So we also took the opportunity to measure actual wines. We measured red wine and white wine. We measured alcoholic wine and non-alcoholic wine. And mixed it with saliva, of course, like we did in our previous experiments. So for red wine, we found a friction coefficient increase of 0.2 compared to saliva alone. And for alcohol-free red wine, the friction increase was 0.5. So the friction increases with red wine because of the presence of tannic acid or tannins in red wine. Now, white wine contains very limited tannins and is also not known to give a dry mouthfeel. So let's have a look at what that does to the friction coefficient. With white wine, the friction coefficient increases with 0.1. And alcohol-free white wine, the friction coefficient increases with 0.2. So what we see is that red wine gives a higher friction coefficient than white wine due to the presence of tannins. And we also find that having more alcohol in the system, so that's the normal red wine and the normal white wine, gives a lower friction coefficient. That's because alcohol, ethanol, can act as a hydrogen bond donor as well, just like HFIP that I mentioned earlier. And this, again, prevents the interactions between astringents and saliva. So another strategy to reduce friction is the addition of alcohol, which is also a food ingredient. So that might be an interesting approach as well. So to just summarize, we've heard a lot about wine, astringency, and different materials such as polyphenols and alum. I just like to put everything onto one slide and just summarize some of the main messages. So we've shown that astringency is related to lubrication losses. So it's not, at least for polyphenols, it's not likely to be only a receptor or a brain response. It is definitely friction related as well. The large polyphenols are able to aggregate PRPs and mucins, so both of the salivary proteins. And we've also seen that just aggregating mucin is not enough to induce lubrication losses, especially when PRPs are present as well. And we've also shown that lubrication losses can be prevented by adding a hydrogen bond donor, such as HFIP or ethanol, or by adding a viscous component, such as glycerol. So I hope that you enjoyed this talk and that you now have a better idea of what happens in the mouth when you experience certain mouthfeels, specifically the dry mouthfeel, commonly referred to as astringency. So I would like to let you know, first of all, that this article where we explain more details of this work has recently been accepted for publication. If you'd like to know more details, you can very soon find this in Food Hydrocolloids. I'd like to thank my colleague Philip Furman and the students Roos, Avi, and Ilse who have contributed to this work. And I'd like the Graduate School Vlag for funding my PhD. And I'd like to thank you for joining in, not only to my talk, but for supporting this entire movement that has been started. Thanks everyone for watching. Thank you for having me. Thank you for inviting me. And if you have any questions, any suggestions, any feedback, as I mentioned at the beginning, if you have any suggestions on career opportunities, do not hesitate to send me an email. And if you're interested in some of more of the specifics of this work, do not hesitate to contact my supervisors, as I myself have recently completed my PhD and also, left Wageningen University already. So Hopefully this has been very insightful. And once again, thank you very much.